Welcome back. Off we go. Here we're going to react ethers with acids. And we're going to have similar questions that we've been having. All right. We're going to have similar questions that we had earlier about which direction we should go. Here we'll go with HI. I haven't used HI too much this semester. Very good strong acid. We're going to use excess of it. And we're going to generate three products. One of the products is H with O in the middle. Yep, that's water. The other two products, tert-butyl with an iodide. I'll put the iodide on in a second. And 1, 2, 3, 4, a butyl group with an iodide as well. And I bet you could figure out the mechanisms for this and this on your own by now, but we're going to do them anyway. Acid-catalyzed hydrolysis, instead of HI, you're going to use HOH. And take a wild guess what your catalyst is going to be. That sentence I said earlier does not change. Hot SOR H2SO4. And colors here. You got your alkyl groups in black. And hydrolysis. I think I gained a carbon on that bottom one. Yeah. Don't do that. And we have OH over here as well, except it should be the green OH. Thought I hit the green. We may have to change the color scheme as we go. Let's do a clean version without any mechanisms and put the mechanism underneath. As you might guess, to get things started, to have things leaving eventually, you need to protonate the O. Recurring theme in oxygen chemistry. One way to make an O a better leaving group is to protonate it. And that generates this intermediate, tert-butyl, O-butyl, with a new H on it. Oxonium, leaving group. Question: which carbon do you want it to leave from? The tertiary carbon on the left to generate a carbocation, or the primary carbon on the right to generate, don't even say that sentence. I do not want to see primary carbocations, ever. So I think I answered my own question. Next step, generate the tertiary carbocation. Primary carbocations are haram. They're forbidden. And shrink my arrow down a little bit. Looks like I need a teeny bit more room. Tert-butyl has an OH on it. No, tert-butyl doesn't have an OH. Tert-butyl's the cation. Right after I just asked you what happens first and why, I went against it. H bonded to O, bonded to butyl. And we generated I- in our first step. Nice nucleophile I-. One of our products is accounted for. I- makes sigma bond to carbocation, generating this product over here. Somehow we have to make this alcohol into this alkyl iodide. Well, alcohols, they don't have good leaving groups on them. How do you make the O into a better leaving group? You used your second mole of HI. Protonate. Iodide will find a use in a second. Iodide nucleophile will have a different fate than our previous iodide nucleophile. Here's your O with 2 green H's on it. I wonder. Attached to a butyl group. 1, 2, 3, 4. I have a primary carbon with a leaving group right here. Primary carbon, excellent leaving group, strong nucleophile. That combination, I have no choice, SN2. You're not going to make a carbocation. Do not say SN1. Backside attack on the primary carbon that has the leaving group. Leaving group leaves, generating these last 2 products at the same time. So we generated this product here and that product there. And I think in my original, I forgot to put a plus sign saying 3 products. Yeah, there was a plus sign right here. The mechanism below, very, very, very similar. Shorter. Starts off exactly the same. You're not going to use water as the acid. Sulfuric acid or HOTS does the same thing HI did. Generate an oxonium. Generate the tertiary carbocation. Got it? Yeah. Water's going to attack. Water, reminder, water's the solvent and the nucleophile. Solvent and nu. Let's just wing it. We protonated. We can use HOTS. And black arrow, why not? Terbutyloxonium. In fact, I want to do everything in black here. Choice of primary carbocation or an SN2. You're going to always go with the, tertiary carbocation or SN2 on the primary carbon with a leaving group. I always prefer tertiary carbocation. And we generated our product over here. It left. How do you like them apples? How are you going to get the OH on there? Water. It's everywhere. Comes all the way to the carbon, generating the conjugate acid of our tert-butyl alcohol. What's going to grab that H from that oxonium? It seems to me we haven't used OTS minus yet. Acid-catalyzed hydrolysis. We better be regenerating our catalyst, or else we haven't understood what catalyst means. And now we're indicating we understand catalysts are remade after they're used. And hydrolysis of ethers gives 2 alcohols. What did reactions of ethers with HX, hydrohalous, HCl, HBr, HI? There's another name for that. HX is doing this to the ether. It's cutting it. Cleavage of things is to cut them, like the implement in your kitchen called a cleaver. Cuts things apart. Okay, blank pages, just in case we needed them. I decided against it. This is our final topic of the semester. And I just I can't make this clear enough. This is the most important section in chapter 11. This is the most important section in chapter 11. And we're going to make that big purple and huge. And there you go. I'll just do a brief introduction here, and we'll just do one more segment today. So we're going to cut the day short. We've all got things to do. And we're going to do two major types of reaction. React that up. That's an epoxide, by the way. How do you know it's an epoxide? It's got an ether inside of a triangle. If I was a better artist, you'd see the triangle right there. Yeah, it's good. And if we use the strong nucleophile approach, strong new approach, like say we use this nucleophile here, OCH3 minus, that's a nice strong nucleophile. And we have HOCH3 there as well as a solvent and a source of protons. You are going to see the OCH3 end up here. The old O stays on the more substituted position. It picks up a proton from the solvent, and we have a carbon group here. And then there's the acid-cat approach. Acid cats having a big day today. And what's our favorite acid cat? H2SO4 or HOTS. And in this example, I'll also have HOCH3 present again. This time it's going to serve as a weak nucleophile because there's no other nucleophiles here. And the solvent. So in both examples, it happened to be the solvent. And an interesting result occurs. The epoxide O stays here and gets an H. And the OCH3 ends up here. And for those of you upset that we had a reaction with a triangle and I showed the things being syn, even though it wasn't really an issue when it's acyclic, I'm just going to clean it up. And I know you like to see it anti every time you pop open a triangle. So when we come back, we're going to do the mechanisms for both of these and then a summary of all the possibilities for each approach that you will be responsible for on every exam in Orgo 2. So I'll see you very soon. We're almost there, everybody.